Autonomous driving of truck-trailer mobile robots with linear project control for trajectory following. Truck-trailer vehicles are used in different fields of industry. They are a faster and cheaper transportation means of people and cargo than individual vehicles. In this paper, we want to solve the following problem: how to make a truck-trailer vehicle autonomous and driverless, becoming a mobile robot. Truck-trailer mobile robots are complex systems because they are highly nonlinear, highly unstable, and their actuator are non-holonomic. Even more, there is a restriction in the magnitude of the truck-trailer angle. The angle between the truck and trailer should be kept small in order to ensure the controllability and maneuverability of the vehicle. Mobile robots are difficult to control, especially in backwards motion. Here we present the problems we want to solve in this paper: positioning control and trajectory following. In positioning control, we want the mobile robot starting from different initial positions should be able to achieve this final desired position. And also in trajectory following, we want that the mobile robot starting from different initial positions is able to follow with high accuracy this linear trajectory, as well as to follow with high accuracy this circular trajectory or any other type of trajectory. For solving this problem, we will formulate the model of the truck-trailer mobile robot. Here we have the truck, the trailer, the steering wheels, front wheels, the traction wheels, and the rear wheels. Here we present the bicycle model of the mobile robot. This is the truck, this is the trailer, two articulated bars. X, Y are the coordinate of the rear center of the trailer. Theta 1 is the inclination angle of the truck. Theta 2 is the inclination angle of the trailer. Theta 1, 2 is the angle between truck and trailer. We want to keep this value small. And delta is the steering angle of the front wheels. It is the control input. The model will be formulated considering the following assumptions. There is not slipping, no skidding. The robot moves at low speeds, less than 3 meters per second, and the speed is constant, and the robot moves in backwards motion. These equations represent the kinematical model of the truck-trailer mobile robot. Here we have the time derivative of x, y, theta 1, theta 2. And theta 1 dot minus theta 2 dot, we can obtain the time derivative of theta 1 dot. Here, tangent delta is the control input, and we will use these nonlinear equations to formulate, to design the linear Fuzzy controller. First, let's start with positioning control. We want the mobile robot to be able to achieve this final decided position without colliding with the obstacles at both sides of the decided position. These are the values of the decided position. X asterisk equal to 80, Y asterisk equal to 0, and angle theta 2 asterisk and theta 1 2 asterisk equal to 0. Also, we have to fulfill the following restrictions. The steering angle delta should be in the range between minus 30 degrees and 30 degrees, and the angle between truck and trailer, theta 1 2, should be minus 60 degrees and 60 degrees in order to avoid undesired jackknife positions. For the positioning control problem, we will apply the following control strategy. In order to avoid collision with obstacles, the robot will prioritize achieving the line y equals 0. Here the robot achieves the line equals 0, and afterwards it will move straight forward to the desired position. Applying this control strategy, coordinate x is not required for control, and the desired position is given by these values. This figure shows the block diagram of the control problem. Here we have the mobile robot with input the steering angle delta and output the values of the present position, which are input to the driver, together with the values of the desired position. This information is used by the driver to compute the steering angle delta at each instant of time. The nonlinear equations of the kinematical model of the mobile robot will be used for designing the Fuzzy driver. Here we have the nonlinear model, And we will linearize this model around this desired position. And we can obtain this linear model of the mobile robot. Here, tangent delta is the control input, and the state vector is given by y, theta 2, and theta 1, 2. B is the speed of motion, and L2 is the length of the trailer. Using this linear model, we can formulate this linear control law, which is valid around the desired position. Here, coefficients K1, K2, and K3 are chosen to stabilize the linear system. However, this control law will be valid only if theta 1, 2 is small. This is the linear range. And we have a problem. What to do when theta 1, 2 has high values far from the linear range? What we can do in order to control the system, control the mobile robot, avoiding jackknife positions. Here we have two examples of jackknife positions. In this case, and also in this case, the vehicle has get trapped into jackknife positions with an angle theta 1, 2 over 120 degrees. We want to control the mobile robot in order to avoid jackknife position. Our objective is to have an angle theta 1, 2 with values in the range between -60 and 60 degrees. In order to do that, we will partition the range of theta 1, 2 in 3 partitions. Here we have the central partition, we call it 0, and it corresponds to small values of theta 1, 2, the linear range. And here we have this partition, positive big, corresponding to high positive values of theta 1, 2, close to the jackknife position, 90 degrees, and it belongs to the non-linear range. And here we have this partition, negative big, which also belongs to the non-linear range and is close to the jackknife position, -90 degrees. And for these 3 partitions, we apply the following control rules. If theta 1, 2 is small, 0, we have to apply the linear control law we presented before. If theta 1, 2 is positive big, this partition, we have to avoid jackknife position -90 degrees. And if theta 1, 2 is negative big, our objective is to avoid jackknife position -90 degrees. So our problem here is how we can avoid these jackknife positions. For this, we will formulate the Fudge control rules. But for doing that, we will apply the robot model for the relationship between angle theta 1, 2 and the steering angle delta, given by this expression. Let's analyze what happens if the angle theta 1, 2 has a high value close to 90 degrees. Since we want to avoid jackknife position, we want the value of theta 1, 2 moves from 90 to a small value. So it has to decrease the value from 90 to 0. It means that the time derivative of theta 1, 2 should be negative. And if it's negative, and since there is a minus here, tangent delta should be positive. And from this analysis, we can formulate the first Fudge control rule. If theta 1, 2 is positive big, then the steering angle delta should be positive, the highest positive value. Making a similar analysis for negative big, if theta 1, 2 has a value of -90 degrees, we want the value of theta 1, 2 moves to 0. It has to increase the value from -90 to 0, so that the time derivative of theta 1, 2 should be positive. If this derivative is positive, and considering the minus here, then tangent delta should be negative. And we have this control rule. If theta 1, 2 is negative big, then the steering angle delta should be negative. And for the central partition, if theta 1, 2 is 0, then we will compute the steering angle delta using the linear control law we presented before. Here we present some results of applying the integration of linear and fuzzy control law for the positioning of the mobile robot. In this case, we have this final decided position, and we apply this control law for the linear range. And we can see that the robot achieves this final decided position collapse both sides. Here we have changed the final decided position, which now is y asterisk, theta 2 asterisk, theta 1 2 asterisk, delta asterisk. And also we change this control law for this control law. We can see here that y has changed to y minus y asterisk, theta 2 has changed to theta 2 minus theta 2 asterisk, the same for theta 1 2 here, and also the same for tangent delta, which has changed to tangent delta minus tangent delta asterisk. It's important to emphasize that the values of the y asterisk, theta 2 asterisk, theta 1 2 asterisk, and delta asterisk are to be taken to be physically coherent. In other words, they have to be achievable at convergence. We have analyzed the effect of the membership functions of theta 1 2. Here we have two fuzzy controllers. Fuzzy 1, the blue line, with the central partition, considers a wider linear range and a smaller non-linear range. And also we have the fuzzy controller 2, broken red line, considering a central partition, smaller linear range, but a wider non-linear range. Here we present the trajectory of the mobile robot for fuzzy control 1 and fuzzy control 2. We can see that for fuzzy control 1, the mobile robot achieves the final decided position faster than fuzzy control 2. But also for fuzzy control 1, the values of angle theta 1 2 are higher than for fuzzy control 2. But in both cases, jackknife positions are avoided. We have applied the linear fuzzy control also for the mobile robot to follow decided trajectories. In this case, we have a linear trajectory, and we can see that the mobile robot follows this trajectory with high accuracy, starting from different initial positions. In this case, we have also applied the same control law for the linear region, but with appropriate values of y asterisk, theta 2 asterisk, theta 1 2 asterisk, corresponding to this linear trajectory. Here we show the results of the mobile robot starting from different initial position and following this circular trajectory. In this case, also the robot is able to follow this trajectory with high accuracy, and we have applied the same control law for the linear range, but with the values of y asterisk, theta 2 asterisk, theta 1 2 asterisks appropriate for the circular path. Here also we show the trajectory of the mobile robot for sinusoidal decided path, and we can see that the control law, the fuzzy control law, is able to make the robot to follow this decided trajectory with high accuracy. We apply the same control law for the linear range, but with the appropriate decided values. With these results, we verified the effectiveness and performance of the integration of linear and control and fuzzy control rules for the autonomous motion of mobile robots working in different operating conditions and for achieving different final positions and also following different types of decided trajectories. With this, I finish my presentation. Thank you for your attention.